Okay, so here's the second part of our discussion on probability. I combined 3-2 and 3-3 together and just called it basic rules. The rules and definitions that we need today. The probability of two events, A and B, will occur in a sequence is read like this. The probability of A and B is equal to the probability of A times the probability of B, given A has occurred. So let's write that down. This is read the probability of event B occurring if event A has already occurred. Second rule I have listed is the probability that or. So here we have and, here we have or. So probability A or B happens is the probability of A plus the probability of B minus the probability that both would happen. So try to keep this in mind. And is multiplication and or is addition. That should help a little bit. Okay, now let's move through these. The last thing I have noted is another definition over here to the side called mutually exclusive. Two events cannot occur at the same time. So if you notice, this first Venn diagram has a picture of mutually exclusive. So this would be that the probability of A and B happening at the same time is 0. This one, this piece right here, this dark purple piece, is the probability that they both happen. So they overlap, right? Okay, now I don't know that all of these examples are actually the best ones in the world. So I think I'm going to throw out Richard Nixon. I'm not in the mood to talk about him anyway. Most of you weren't alive. So let's move to blood types. So I'm going to look at blood types. The probability that a person in the U.S. has type blood B positive, ha ha ha, B positive, I get it, instead of B negative, har har. Okay, B positive is 9%. 5 unrelated people are selected. Find the probability of blah. Okay, so let's start off with what we know. We know that the probability of our event is equal to 0.09. Question is, what is the event? The event is picking what? A person with B positive blood. Okay. Now, I want the probability that all 5 have B positive. So that's the probability that person 1 is a success, and person 2 is a success, and person 3 is a success, and person 4 is a success, and person 5 is a success. Now, and means multiplication. The only catch is, what are you multiplying? Well, 2 events, or in this case technically 5, because you have 5 people. And does the probability of the second event depend on the first event? So if you look, that's the whole reason for this unrelated. They're not related to each other, so everybody has the same chance. So the probability would be 0.09 for the first one, 0.09 for the second, third, fourth, and fifth. Now, we know the shortcut to that is this, right? That would be nice if I actually wrote it that way. And it's teeny tiny, 0.000006. Whoa, almost not happening at all. The second question says, what's the probability that none have type A? So this was part A, and now we need part B. I need more space to write. Plan ahead, Maeve. Okay, so part B. Find the probability that none have B positive. So if 9% have B positive, 91% don't. So then this would just be a situation of 0.91 to the 5th power. That's way more likely. All right. Is this the complement to part A? No, because they should sum up to 1. All right, part C says find the probability that at least one has type B positive. Now listen to me because I'm not writing this down. That would mean that maybe the first person has it, nobody else does. Or the second person has it, nobody else does. Or the third person has it, nobody else does. Or what about person 1 and 2 have it, but nobody else does? Or what about 2 and 5? So there's all kinds of combinations. That's not a really good idea. This is actually the complement to the answer we got in part B. The probability that none of them have it versus at least one of them have it. So in order to calculate the probability for part C, we just need to do 1 minus the 6240, and we get 0.3960. Our last question talks about being unusual. And if you've read your book, you know that unusual means less than 5%. And so part A is an unusual event. All right, let's try another way some of this would be asked. So I have a chart for us, and looking at our chart, always look at the chart before you read the problem. I'm looking at level of degree, and I have associates, bachelor's, master's, doctorate, and then a total. I have it broken down by male and female, and then also a total. And the numbers are in thousands. You see that right here? Numbers are in thousands. And this is old data. All right, so a person who earned a degree in 2004 was randomly selected. Find the probability of selecting someone who earned a bachelor's degree. So we come in and we say, okay, how many people earned a bachelor's degree? So we come over here, and the number we want is right here. And typically, your probability can be done by simply just saying, what's the part I care about over the total? Not always, but. So in part A, I can take the part I care about, which is the 1322, and divide by the total number looked at. Now these are really in thousands, but the thousands would cancel out, so we're good. And you can convert this to a decimal, but I'll be honest, I don't really care. So I'm going to leave it like this because I'm lazy. Part B. Earned a bachelor's degree given the person is a female. Now given means that you're only allowed to pick from that category. So it said, given the person is a female, means I can only look at the female column. That's right here. All right, and what did I want? A bachelor's degree? Well, where are the bachelors? So bachelor's degree for a female, and then the total for a female. So we have 769 divided by 1460. So see again, the part I care about divided by the total seems to be helping me out. All right, let's try again. Love my eraser, by the way. Okay, I've earned a bachelor's degree, but given that the person is not a female. Now that's just dumb. What else is there? Oh yeah, males. Okay, so same situation. The 553 divided by the 1006. So that's boring. Let's look at the next one. It's got an or statement in it. Uh-oh. Living on the edge here. So right here, or, right? So I want an associate's or a bachelor's. Does it have anything given to me? No. So I get to choose out of the total, the 2466. But I want an associate's or a bachelor's. So here's my associate's. Here's my bachelor's, and nowhere on here does it talk about that you could have both. So for part D, all I have to do is say, well, I need 632 divided by 2466 plus 1322 divided by 2466, and I'm good to go. We've done something similar to E, but let's look at this one. So I'm going to go to F. F says the probability that it's a master's or a female. So to be or, you do this. The probability that it's a master's plus the probability that you're a female minus the probability that you're both. Now there's not always a both. So like in part D, associates and bachelors, there wasn't a both. So that would have been a minus 0. So what's the probability of getting a master's? So let's come in and highlight that. Probability of getting a master's would be this. Oops, just kidding. Just jokes, folks. Oh, hey, that rhymed. Probability of getting a master's would be the 467 out of the 2466. Is anybody writing this down? 467 out of the 2466. And then what was the other piece I wanted? Whether I was a female or not. So I come in and I look at, to be a female was this much. So let's write that part down. I have the 467 out of the 2466. Now I'm going to add the 1460 out of the 2466. But anybody that got a master's that was a female got counted twice. Got counted in the master's piece and the female piece. So now I need to subtract out the both part. The both is right here. So that's 270 out of the 2466. And I think we've beaten that question to death. So I'm done with those examples. Moving on to question 4. These are probably more likely the ones that you'll see on test day. Well, that's not true. I'm lying to you. But if I'm going to pick something for final exam date, how about I say it like that? And it's got a typo in it. Right here, we're dealing with care, and I really mean the word card. Card is selected at random from a deck of 52 cards. How would you calculate this? So I'm going to do the probability that I got a club plus the probability that I got a 3 minus the probability that both happen. Well, how many clubs are in the deck of cards? There's 13 out of 52. How many 3s are in the deck of cards? 4 out of 52. How many 3s do you have that are clubs? 1 out of 52. So you do need some prior knowledge to work these problems. Fair, not fair, I don't know. Go buy a deck of cards and play with your grandma. Okay, randomly selecting a 7 or a face card. So what's the probability that I randomly select a 7 or, so that's addition, I randomly select a face card. So what's a face card? A card with a face on it. Jacks, queens, and kings. So a 7, there's 4 of those in a deck. Face card, jacks, queens, and kings. There's 4 sets, so that's 12. And then how many are both? Well, none. So ta-da, we're done with him. Okay? What else? I think that's about it. I know there's more to talk about from this chapter, but that should get you guys started in chapter 3, and we can talk more when I see you, wherever that might be. Thanks, bye.